Thank you for coming to my talk. This is GreedyBTS, which is some adventures in GSM hacking. So yeah, I'd just quickly start off by running through the agenda. First of all, I should give an introduction to who I am. And then we'll go through an overview of 2.5G mobile environments. We'll discuss cellular diagnostics and tools. We'll also cover security weaknesses within GSM. And then we're also going to look at how to build an open source 2.5G simulation environment for doing technical analysis in. And then we're going to look at how we can use that environment to implement attacks against GSM environments. And then we'll do a demonstration of an attack tool, GreedyBTS, which I've created for the purposes of targeting 2.5G environments. So my background is as a penetration tester. I've been a penetration tester for around the last sort of 10 years. And I've been avidly researching computer security topics and have published a number of exploits and vulnerabilities. And I've got a strong interest in radio and embedded systems. So first of all, I'd like to give a bit of an overview of GSM and what it is from a technical perspective. So this is a little bit in-depth and technical, but it's necessary background understanding to realize how the attack tools do what they do. So it was introduced in June 2008. On June 2008, there was around 2.9 billion subscribers who were using GSM. And it replaced the total access communication system in the UK, which was the older legacy analog environment, which was vulnerable to snarfing, where people would take ESNs and MINs and reprogram them into phones for cloning users' bills. So it's a European-wide standard, which was started in 1982 by Group Special Mobile, and that has security features in it that were introduced to prevent the losses that they were sustaining on the mobile phone companies due to a wide range of fraud. GPRS was created to work within the GSM standards and address the data needs for the always-on connectivity, which had a high price of constantly dialing up over the existing GSM standard. And that's how you got the 2.5G environment. UMTS and LTE are third and fourth generation networks, which are now widely on the air. And we still have 2.5G within those environments for legacy purposes and as fallbacks. So I wondered how vulnerable 2.5G networks and GSM communications are today. So this is an overview of the 2G GSM architecture. We can see here that the mobile station, or ME, is your mobile phone, and it consists of the mobile equipment and the SIM card. And then this is the link to the BSS, which provides the air interface between the network and the phone. And that's the base station subsystem, which comprises of the base station controller and base transceiver system. There's the network switching subsystem, which provides authentication, identity, billing, and more. And that's basically what a 2G environment looks like by itself. So a mobile station, which is your typical cell phone, it has an International Mobile Station Equipment Identity, otherwise known as an IMEI, and that contains uniquely identifiable information on your device. You also have a SIM card, which contains your subscriber information. Your SIM card contains what's known as an IMSI, or International Mobile Subscriber Identity. And this starts with a mobile country code, which is 3 digits, a mobile network code, which is 2 digits, and then your mobile subscriber identification number, which can be up to 10 digits and is otherwise known as an MSIN. The SIM card also holds encryption keys, which are used for air encryption and authentication. And the phone itself contains a baseband processor and real-time operating system for use by GSM. And it's essentially just a radio device. So the SIM card, what is a SIM card? Basically, the SIM card is described in GSM 11.14, and it's known as a subscriber identity module, which stores both the IMSI and KI key. The KI key is needed for network authentication and also air encryption. You can get programmable cards which can be used with a writable KI key, or you can buy GSM test cards with a writable KI key for being able to write that KI key value in if you want to do authentication. And this diagram here shows how you can actually use a PIC microcontroller and implement a SIM card for GSM purposes on top of the PIC chip. So that basically this comes down to ISO 7816, which defines the physical smart card standard. It then implements a SIM toolkit or SIM application toolkit, which is implemented by the smart card. The GSM application which sits on top of that is what implements the authentication APDUs. So some known weaknesses within smart cards was Comp128 version 1, which was an encryption algorithm that was found to be flawed. And essentially that was because of a stop condition that allowed for the brute force attack to be leveraged against the SIM card to disclose the KI key over a period of time. That can take a 12 to 24 hour period and requires physical access to the SIM card. And now it's been replaced by Comp128 version 3, which is much more widely used, and the Comp128 version 1 is fairly rare. You can find Chinese vendors who will sell the cheap Comp128 version 1 multi-SIM cards and cloners, which are essentially made for making a backup of your SIM card. There's also the Osmocon SIM trace utility, which is worth a mention because you can essentially man in the middle and trace the APDU activity between a handset and a SIM card. And the THC also have a SIM toolkit research group that contains a lot more information on SIM cards and SIM card vulnerabilities. Well, this talk's not really about that. It's more about the base transceiver system, or BTS. So it's more looking at the transmitter and receiver equipment, such as the antennas and amplifiers. A BTS has components for doing DSP and digital signal processing. It contains functions for radio resource management and provides the air or interface to a MS or mobile phone. This is part of a typical cell tower that's used by GSM environments. And the BTS provides the radio signaling between the network and the phone. Inside the base station subsystem, there's an additional component, which is the base station controller, which provides your logic and intelligence for actually implementing the GSM communications. So radio and cellular. So basically, the GSM spectrum has a chunk of the electromagnetic spectrum, and it's divided up into uplink and downlink channels. This table here actually shows you the different bands that are assigned for 2G GSM use. And then the ARFCN is the absolute radio frequency channel number. And the way that works is essentially the spectrum is divided up into channels, and these channels are assigned a unique number that the GSM can use. And the cellular network is used by different spatial areas, or space division multiple access. And this essentially allows us to use one frequency in one area and then use a different frequency in another area and then reuse the same frequency elsewhere by dividing the environment up into different spaces. At the physical layer, the physical layer 0, you actually have this, layer 1, sorry. You actually have this waterfall views of what a absolute radio frequency channel, RFCN, looks like. So on the left-hand side here, this is what a GSM downlink looks like. And on the right, we have a GSM uplink. This is divided up into 200 kilohertz channels, which is then split into time division multiple access slots. So you have time slots within these channels that are assigned resources. There are different bursts which are then encoded within or modulated within this radio space. So GSM communicates, as I mentioned, with time division multiple access or frequency division multiple access, which is TDMA and FDMA principles. This here re-shows the spatial division multiple access that's being used to give this, you can use one frequency in one area, and then we can see that we can reuse it in another area by dividing up the space used for the frequency. The traffic is transmitted as bursts, and the modulation is using Gaussian minimum shift keying. Gaussian minimum shift keying is a variant of frequency shift keying, which has been designed to reduce the bandwidth that's required. So that is then known as minimum shift keying, and then it's applied with a Gaussian bandpass to further optimize it for spatial use. So the actual network switching subsystem, which is the more of the back-end environment, we have the network components that are usually not accessible or visible to an attacker. They are the mobile switching center, or MSC, the home locality register and visitor locality register, which can be looked at as forms of databases, and the equipment identity register, or EIR. So these handle information on the subscriber. They hold things like the IMEI values, encryption keys, and then back-end processes will do things like billing and charging against a user who's placing calls. It's also where the call switching and routing takes place when you're connecting to other networks. So, for instance, connecting to a public switch telephone network would all be performed in the network switching subsystem. GSM is divided into what's known as logical channels to allow for signaling between the handset and network. There's a defined traffic channel which has full rate and half rate channels available as traffic control channels, full rate and half rate, or BM and LM. There are also signaling channels known as DM. And a lot of the weaknesses that have been found in GSM to date are due to this problem of in-band signaling, which is essentially the mobile station and the base transceiver station are signaling within the same channels that they're using to sort of manage. So they're divided up logically into different channels, but they're accessible to the mobile phone. It's this same class of vulnerability that allowed Freaka blue boxes to function and has been responsible for format string attacks. And it's also basically, when management capability is accessible, it's got the potential for subverting. So anywhere where you can get access to management information, you've got a potential to exploit it. So the various logical channels that are created, we have the broadcast channel. Now the broadcast channel is used by a mobile station to synchronize the oscillator and frequency with the base transceiver system so that they're able to communicate more accurately and encode information and speak to each other. The BCH consists of subchannels that assist with that process, which includes the broadcast channel, the frequency correction channel, and the synchronization channels. The channels are used during the preliminary station of a mobile station being powered on, and they're an integral part of what we would all refer to as getting a signal. So there's also the common control channel. The common control channel is used by a mobile station and BTS for communicating requests and resources. And it's essentially used for making a request to say, I want to make a phone call, so it makes a random access channel request, and then there's the access grant channel or paging channel and notification channel, and it's used for notifying the mobile station and asking and requesting for resources. There is also the temporary mobile subscriber identity, which is used to help prevent the tracking of a GSM user, that can be frequently changed by the BTS. Usually has a configurable lifetime, so it's assigned to you and eventually will expire and you'll be given a new one. There is the dedicated control channels, the DCCH and its associated subchannel, which is used for authentication, cipher selection, and signaling of call completion. And this has a breakdown of dedicated control, associated control, slow associated control, fast associated control. And these basically are used for this authentication, selection, and signaling that the call has been terminated. So the attacker can actually exploit GSM signaling weaknesses to access a subscriber's mobile usage, and we're going to look at this in a little more detail. But first I just wanted to talk a little bit about the over-the-air encryption. So there are several over-the-air encryption algorithms that exist, and they're used to encrypt some of the GSM data that goes in those channels. It's not all of them. So for instance, things like the traffic channel and voice communication are typically going to be encrypted. So there's A5/1, which has been publicly broken. You can download rainbow tables for it. There's A5/2, which is essentially no security whatsoever. And then there's the A5/3, which is the Kazumi cipher, which is vulnerable to a number of man-in-the-middle attacks, but it's not yet been publicly broken when applied in GSM. There's also A3 and A8, which is used during the authentication process. And as is widely known, an attacker can attempt to passively analyze traffic looking for weak encryption or perform man-in-the-middle attacks against subscribers, mobile phone and base transceiver station. So there's also now the General Packet Radio Service. General Packet Radio Service, or GPRS, is what makes a 2G GSM environment 2.5G. It makes use of existing GSM concepts such as time slots, and introduces two new components into the original GSM architecture, which is the Subscriber GPRS Service Node, or SGSN, and Gateway GPRS Service Node, or GGSN. It adds a packet control unit to the base station subsystem, and then basically data is then sent in these PCU frames, and it introduces new radio resource protocol management, which is separate to what's being used by GSM. And on top of that, it builds the radio link control and media access control for allowing packet data to be sent within the GSM time slots. Okay, so that's kind of a bit of a detailed technical overview of the background for 2.5G. So what I'd like to do now is just sort of give you an overview of some of the tools that you would use to begin analyzing a cellular environment. So the first tool I would look at is the Nokia NetMonitor. So Nokia shipped a diagnostic tool in early phones, particularly here shown the Nokia 3310, that you can enable a hidden option called NetMonitor. And this basically allows you to perform things like absolute radio frequency channel number identification that you're connected to. It'll show you things like the channel that you're on. So here we can see the common control channel. You can also do things like capture the uplink traffic that's being sent through your phone. It's basically a very cool feature of Nokia and quite widely used because of its versatility, even within the mobile providers themselves. There's also dedicated test hardware. Now I spend a lot of time on eBay trying to find test hardware for GSM. Here's an example of a GSM Analyzer I purchased. The prices can vary quite widely. You can get things that cost a few £100s to things that cost in the tens of thousands. And they're actually not very well featured. They're quite restricted. The cost can be quite high. If you try to contact the people who manufacture the hardware, they're generally not going to help you unless you're a large-scale monopoly. And actually, open source tools are a lot more flexible these days. You can do a lot more with some of the open source stuff that's available. So one of those open source tools is the Osmocon BB that allows you to write tools essentially for a mobile station's baseband. For instance, the Calypso Texas Instruments chip, which was leaked, they have essentially reverse engineered that and been able to ram boot their own utilities on there so that they can get access to the baseband and implement pretty much anything you want. There's a number of useful diagnostics tools already available that you can download. And you can extend the code to visually represent the GSM Spectrum with only a £30 phone. So here on the right of the screen, this is actually a GNU plot where it's taken power measurements of all the GSM channels within the GSM 900 band and then just visually represents them. And although it doesn't do it in real time, you can just sort of capture these measurements and you can actually view it and see what the spectrum looks like, sort of like a spectrum analyzer, but just for the GSM channels in use. There's also GSM Tap, which is useful for debugging the radio interface. You can access that through these open source tools. It'll encapsulate the radio frequency information and transmit it within UDP encapsulated packets. And it allows us to see the or air interface from either the base transceiver station or the MS mobile station, depending on whereabouts you position it in the environment. And it's quite a useful capability when you're trying to analyze GSM environments to see what is actually being sent in the signaling channels. There's also AirProbe. AirProbe is a utility that's designed for essentially capturing the radio spectrum of a GSM RFCN. And it's a toolkit for analyzing the burst and performing decoding of it that will then fire it back out in GSM Tap. And you can actually see what's going on over the air as a kind of passive sniffer. You can do this with a £20 Realtek SDR dongle. It's purely passive and it allows for identification of call requests, the traffic channel, which should use encryption. And then you can use Kraken with the rainbow tables for A51 if you come across that to essentially decrypt information. And Wireshark can parse the information of these cell diagnostics tools out. Okay, so these are the kind of utilities that are available for you for doing as you would do any kind of network assessment, really, just for enumeration and assessment and trying to learn what the environment looks like. So we're going to talk now a little bit about some of the weaknesses that are in GSM. So the mobile station power on process is when you power on your phone for the first time. This is essentially what your phone does. It will start a search for the broadcast channel of carriers by performing radio signal strength indicator measurements. It will perform these power measurements by walking across all of the channels that are assigned for the GSM band. And after it's identified a broadcast channel, it'll probe for the presence of the frequency correction channel. The phone will then sync and obtain information from the BTS about the network that it's trying to access. And it will then know at this point whether or not it should start monitoring the neighboring cells or trying to connect to that network if the cell has identified itself in an appropriate way. And essentially this whole process is unauthenticated, and it's essentially what's being exploited by IMSI capture devices and fake BTS attack tools. So to do this IMSI capture and detection, it's quite easy. During a public LAN network mobile search, or PLN-MS, it's quite trivial. In fact, your phone will do this the first time you turn it on or when it's lost signal completely. So it's only performed during that point, though. After it's got signal, it will monitor the surrounding environment for what's known as path loss criterion and reselection criterion, which is these values C1 and C2. They're dynamic variables that are taken by the phone to determine if a cell nearby to it has actual better radio conditions for it. It dynamically keeps taking these variables, and if it finds that the cell next to it in adjacent that's been decoded from when it's synced with the BTS, it will join that cellular environment. If you manipulate those two values, you can force the mobile station to join the BTS without requiring the phone to power on and power off. And during this request, during this location update request, you can actually request the IMEI from the phone, which is the unique number to identify that handset. So when we're looking at the IMEI, we can essentially look at this as a device fingerprint. This table here shows how an IMEI is actually broken up. It contains a type allocation code at the first six digits, 6 to 8 digits. Which starts with 2-digit reporting body identifier. Now, the reporting body identifier is what's used to determine the country which authorized or allowed this device to be used. So it will say whether it was the United States, China, or England. And the remaining 6 digits will identify the vendor who has actually produced the device. So as this IMEI shows here, we can see that the first 6 values are 013035. So we know that 01 is going to be the United States. So it gives us the United States, and then we know that the manufacturer of this device would be Apple. And in fact, we can actually nail it down to a specific model of an Apple phone. Now, it's very rare that these values are going to be spoofed unless it's an attacker who's in the environment. So if you collect an IMEI, it's quite likely that you're going to have a fairly accurate idea of what that device is, as these are rarely changed. And once you know one, then you're going to be able to use that again and again. So the location update request, this is what essentially is occurring over the air. We can see here that the mobile phone is doing what's known as an IMSI attach. It's saying that, hi, I'm this mobile subscriber. I want to connect to the environment. And then the BTS environment is also requesting that back down from it and saying, oh, OK, I also want your equipment identifier. And we can see here that the subscriber in this case is sending his equipment identifier as leet. So what an attacker would need to do is clone a BTS. To be able to actually do an attack and exploit this condition, we're going to need to simulate certain conditions to get a mobile station onto our fake environment. So we're going to need to locate the mobile country code and the mobile network code of the target phone provider or their roaming agreement. So for instance, if your phone allows you to roam to another network, we could also try to spoof that network. And then we're also going to need to identify the neighbor absolute radio frequency channel that's being used by the mobile station by performing our own PLNS locally in the environment which we want to target. So we would then create a BTS using the values that we've obtained by doing that, and any other parameters that we might want, such as color coding and similar, to match a weak signal that's available to that particular subscriber. And we're going to try and pick the weakest signal so that we reduce interference, so that we're going to essentially look like a good neighboring cell. The phone's going to attempt to join it, but wouldn't actually be trying to join the original cell, as we would be broadcasting on the same frequency. And this creates an environment where a target who is in close physical proximity to the BTS will trigger cell reselection, as the mobile station will essentially see this better environment. So the cell diagnostics tools that we discussed before are what you would use to obtain these parameters to create that environment in a physical locality of your target. So Osmocon BB is a pretty versatile tool. You could also use New Radio or GSM receiver to perform this. It includes a monitor command that allows you to view the bar graph and the transmission strength of the surrounding neighbor cells. So we can see here the serving current ARFCN, we can see the neighboring cells, and we can see the locality area code for these particular cells. So what we would do is we would pick one with a particularly weak signal, and we would take the same values and punch them into our spoofed BTS. there is also random access channel and TIMSI paging requests. Now, these can be performed by a mobile station or a mobile phone trying to attack a cell tower. Essentially, because we have a number of time slots and there's a finite amount of resource available to subscribers on GSM, an attacker could continually request these resources by constantly making demands for time slots, or constantly making demands to say, I want to make a call, I want to make a call, but not making use of those resources until all of the resources are consumed. There's also the temporary mobile subscriber identity, which is vulnerable to a race condition. When the cell tower is paging and saying, hey, where's this mobile phone? You could answer that page and say, I'm here. And then, of course, it will try to communicate with you without passing additional information back to the original phone, who, when it answers the page, won't get it because you've raised the condition for the response. Both of these attacks can be implemented in Osmocon BB, and they both can be used to perform a denial of service of a cell tower. You can essentially consume the resources on it so that people are unable to make calls or send texts. So, downgrade and jamming. So it's kind of known that in the event that the newer networks, 3G and 4G, become unavailable, your phone will still revert back and obtain a signal however it can, so it will go back to 2.5G. So these environments can be jammed. You can downgrade and force a connection. I had the fortune to spend a bit of time in Asia, where seemingly illegal devices are available on almost every market bazaar. And I was able to take some of these devices and have a look and see how they actually worked. So this here on the right is a jammer, which has since been disabled and rendered inoperable. But the concept behind it is that you would overpower the analog components of a radio with a stronger signal to essentially force that radio to not function because it couldn't get the communication out to the signal it was intended. The protocols that are used in newer networks are intended to address this via the fact that they want to be more resilient to general noise or sawtooth jamming, for instance, just jamming a signal and trying to overload it. And from what I looked at in terms of these jammers, there aren't really any that are suitable for researchers or testing purposes. And if you want to simulate their use, you can just disable the 4G and 3G because the Wireless and Telegraphy Act in the UK would really forbid the use of these. The devices themselves are not really designed for electromagnetic compatibility. Their whole purpose is to overload frequencies and essentially jam up the spectrum. So they have really no practical use as researchers or for trying to understand how these works, other than the fact that they exist. And if you were criminally minded, then perhaps you might need to use these in the wild. But as I say, it's not really advised here in the UK. Certainly their use is illegal. So what I want to talk about now is simulation of a 2.5G environment using widely available open source software. So OpenBTS is an open source project created by Range Networks, and they basically implement a GSM environment and also supports now a mini SGSN, so you can implement packet radio. And this is essentially its network architecture. A lot of the components that you would find within a typical GSM environment are being replaced by these SQL-lite databases. So you have, for instance, a database for authentication via a component called SupAuthSurf. You have this store messaging queue for passing information, and a lot of the environment is then configured using SIP. And you have this PBX capability for any kind of call routing or additional information that you might want to do. And you can then have your subscriber registry or your HLR essentially within your PBX, so you could assign users phone numbers and the like. So I made use of OpenBTS. And the way that I did it was I got myself a USRP E100. Now, the USRP E100 is essentially a standalone embedded USRP. It's an SDR that contains a Gumstex Avero, which is a computer on module, which is essentially keeps a Cortex A8 ARM processor with DSP and an FPGA for performing more, focused on DSP as well. I put in the SBX daughter board, which gives from 400 megahertz to 4.4 gigahertz, and it's essentially a 100 milliwatt SDR. So it's not very powerful, but it's useful for kind of doing low-powered tests, and certainly could fill a small environment like this room. And you could then use the GPSDO kit or the clock tamer to provide an accurate clock in line with the GSM standards, so that mobile stations will essentially attempt to camp with and able to correct their oscillator to be matching the radio environment and camp on it. And ETIS Research provide an angstrom Linux image built with new radio 3.6.4.1. So I got this because I thought it'd be really cool to have a BTS that was fully embedded that I could use to start launching attacks. So I could put it in a backpack or stick it in an office environment and just target people and then go away and log into it. So I didn't need a big computer or anything else alongside it. Also found out that I would have to find some way of doing the development of this without causing interference to the surrounding electromagnetic spectrum or the RF environment. So I obtained electromagnetic shielding, or RF shielding, which is essentially this large box here that provides essentially a filter, a frequency attenuation for a chunk of the radio spectrum. And I also put on the front of the radio a 50 ohms load, so that when the energy that's being radiated out of the radio is actually just being absorbed by this ohm load and isn't being radiated as effectively as it would if it was on a band-matched antenna. And then I put a receiving antenna on there for 900 megahertz because I still wanted to hear the phones. I just didn't want to have a high-powered transmission, or I wanted to be able to isolate what I was doing from the rest of the world. Another good bit of advice about when you're doing this is to put a spectrum analyzer outside of the environment and also one inside of it. So you can see if there's any signal leakage from surrounding environment, and then you can shut your experiments down should anything appear to leak. This is a graph. I had some help with some radio engineer friends that essentially shows you the frequency attenuation. And essentially this particular device is fairly effective in the sub-gigahertz range. So not just for GSM, but in general, if you're interested in software-defined radio and targeting data networks and the like, you can actually isolate things around from 1 gigahertz down to about DC. And then essentially you can see what's being leaked at the higher ranges. So now to get on to actual implementation of GSM attacks. So GreedyBTS is a firmware image which you can then install inside of a USRP E100. I spent a lot of time trying to rebuild the angstrom image from scratch with limited success. So essentially what I did was I took the stock image and then cross-compiled new kernel images and additional packages in there, because a lot of the ETIS packages are lacking support for sort of SQLite databases, ODBC, and it's really kind of been developed more as a proof of concept that you could do an embedded base transceiver or similar with it. I also built OpenBTS 5.0 and 2.8 with mini SGSN or packet radio support. I had a couple of issues because there's a lack of support for the E series in the OpenBTS branch, so I had to make some patches and fix things within the code. I also started to weaponize the OpenBTS environment itself. So OpenBTS is designed for running an open GSM network, but it's really good because it's really noisy. So if your target picks up his phone and it says, oh, hey, welcome to your test environment, they're immediately going to be aware that something is not quite right with their phone. So I made some patches to that, such as removing welcome messages, removing functionality which might alert a user to the fact that they're not connected to their normal network. And then I've also increased logging in things like the L3 mobility management for events, so that I can more accurately track what's going on over the air for performing attacks. I also turned off the SGSM's firewalls for GPRS attacks, so that the BTS itself can begin targeting via packet radio any mobile devices that it's seen. I configured the Asterix environment to have full real-time support and automatic logging of any traffic via the functionalities like monitor. I then added a console script for interacting with the various back-end components of the BTS. So, for instance, having the HLR or the ability to add a subscriber dynamically. And then I integrated a number of databases for fingerprinting devices as and when they're seen over the air. And then also for assisting you in cloning a cellular environment. Essentially, this is what is shown to the user. When you launch the GreedyBTS application, you can access it via a console. It shows you the current configuration for the cell. It gives you the various radio power that exists there, and sets up everything automatically. So because it's an embedded device, everything is automatically configured. You just install this stock image inside the device and everything's running for you. All of the useful events that are handy for an attacker are sent to GreedyBTS.log, so that these are logged then and accessed by the console application. And it can dynamically provision a phone based on either the IMSI, so if we know the subscriber's identity, or alternatively the IMEI. So if I know, perhaps your IMEI from an application, or I punch *#06# into your phone, then I can basically begin to target you specifically and nobody but you. And also, because these IMEIs can be used to identify vendors, I can also say, well, I'm only interested in getting Samsung Galaxy devices, or I'm only interested in communicating with Apple iPhones. And this allows me to essentially pick specific classes of devices or people that I'm interested in. I then built a number of useful utilities within the firmware, such as AirProbe, various Osmo tools. I added support for packet analysis, T-Shark, TCP dump, and libpcap. The CDR records from Asterix and the SMQ are used to keep a recording of any subscriber communications attempts. So once you actually give someone service, it'll automatically record information about what they're trying to do. I then added, for Asterix users, you can essentially change and do things in Asterix. So if you want to give them connectivity to the PSTN, so that when they make a phone call, you can actually connect it to their target destination, or other amusing feats that you can think of with Asterix. I also added the GPRS, so that's automatically configured. If you give the embedded device an internet connection, it will automatically set up the GPRS, and it will automatically give the phone GPRS if it's capable and asks for it. And as an example for what we could do with packet radio, I added a background exploit that just systematically waits for devices that match an Apple iPhone, and then it will attempt to use exploits to compromise that mobile station and exfiltrate the data back to the embedded device so that I can browse through their phone book or text messages. The exploit's not particularly sophisticated. It's quite a slow attack to do. So it's just there just as a kind of proof of concept. You could attack, for instance, the mobile browser or other components, but you need to be aware that attacking over GPRS is kind of a slow process and can take some time. GreedyBTS is essentially designed to be used against a particular target. It's an embedded device. It's got you're not going to be able to get 500 users making phone calls through it. But for instance, picking 1 or 2 people and then monitoring what they do, so whatever text messages they're sending, whatever phone calls they're making, whatever internet sites they're trying to browse on their sign, and then on their phone, and then actually trying to attack their phone should they be in the vicinity of the device. So, for instance, you could imagine if you're interested in targeting the CEO or a Fortune 500 company, and you pick a particular individual and you place this device in his office, you're going to have a large period of time where you're going to be able to actually extract information from their phone and profile that individual and their habits. It's Linux, so you can do whatever you want on top of that. This is the help screen or the console that's provided by GreedyBTS. This implements a number of commands that are used for the assistance of targeting a particular individual and doing this over-the-air kind of attacks. And then essentially what we can do is we can set things based on regular expressions, and we can also run tools like our fingerprint tool here, so we can actually see what kind of devices we've seen over the air. And we can also then as well see the output of any of our kind of exploits that are being run. And then it's also got tools for shutting down and terminating and the like. So a quick mention on, as I mentioned before, about GPRS. It actually can take quite a while to exploit things or inject traffic, because you sacrifice the ability to make calls, because GSM and GPRS are making use of the same time slot. So the more data throughput you have, the less capability you have to make calls. So you have to make a balance between how much traffic you want to be able to be put through. And as an example, when I got the iPhone exploit to work, which was basically just trying to SSH into an iPhone that's been jailbroken and hasn't had the passwords changed, and then essentially that will go in and just grab the SMS, grab the context and the address book and store it. And just that process alone can take up to 5 minutes. So if you want GreedyBTS, you need an 8 GB micro SD card. You can basically just download it from this URL here. It's OpenSSL encrypted. If you do want it and you're interested in researching GSM environments, I'm more than happy to share it with you. Just get in touch with me for the password. The reason behind that is that when I started to discuss the things that I was looking at in February of this year on the various mailing lists, I had a number of well-known security researchers who emailed me that weren't really against the fact of creating an image and making it available. It's just more about trying to keep an eye on not sharing it with anyone in the world who just feels like tapping somebody's phone arbitrarily. So if you do want what I've written, that's cool. If you want to make it yourself, there's enough information here for you to go away and do that. But certainly just drop me an email and tell me who you are and why you want it. Having said that, if you are interested in GSM, there's a PCAP trace of GSM over the air. So I captured a downlink and an uplink, and also the information that's coming from a SIM card, and stored that in a PCAP file. So you can essentially just download this PCAP file, get yourself a good book, and have a read through and actually see what goes on over the air on an uplink and a downlink of a mobile station, so you can put it there for review. And also, as an alternative, if you wanted to go away and start implementing this stuff yourself, there are things like the BeagleBone Black or a Nano BTS or B200. You could actually do this thing now for a couple of £100. It's nowhere near the thousands it used to cost a couple of years ago. So that's really why I wanted to do this talk, was just to show that we can, essentially the cost point of doing these kinds of attacks is decreasing quite rapidly, and the amount of security controls or protections just hasn't changed. The vulnerabilities that are being exploited in this way, we have very little defense. There are very few phones that actually will alert you when somebody's trying to do this, and it's fairly transparent to the user, and we can also try to attack them via traditional IP-based attacks. Okay, what I want to do now is essentially demonstrate GreedyBTS by putting a couple of devices inside of this Faraday cage and showing it being targeted. So. Okay. Oh, sorry. Okay, so this is the serial console on the embedded device. Essentially, we've got a USB connection that feeds into this box, but everything that's actually being run is on the actual ARM device itself. So if we were to log in to this device, we can essentially just have a quick look at the IP address as well. So it's running SSH by default, and we've got here a couple of helper scripts and utilities that are designed for assisting us with these attacks. We've also got here the iPhone exploit that we're using for automatically trying to attack a target's iPhone. And if we just sort of SSH in as well. Okay, so essentially by running this launch script, it will load all of the components that are necessary for us to begin simulating and targeting the attacks. And we get here our current cell configuration, the setup for the various radio power, and it'll take a minute or so before we get a GPRS connection. And essentially all that's doing is setting up a virtual TUN interface, giving it IP, and essentially connecting that to the RF side of things, and then routing it out via Ethernet. So you've basically got your GPRS accessible over the air to a phone. The priority messages that are there is essentially I'm trying to increase the amount of processing that can be done on the embedded device for the radio side of things. So everything runs a little bit slowly, but that's essentially so that the phones themselves can be targeted a little bit better. I can sacrifice a little speed in how long it takes to punch in a command for more reliability over the air. Okay, so this is our console interface that provides us with the easy way of configuring these kind of environments for doing targeted attacks or analysis of GPRS. So one of the things that we would like to do is, first of all, we're probably going to want to configure our cellular environment to match something which the mobile device or device under assessment for security analysis purposes. We would, for instance, need the MCC and MMC. So if we punch in list, we can actually list all of the various countries' mobile country codes, and we could also then do a cell find and actually show them for a particular country. So if we punched in the UK, we can actually see all of the necessary codes that we would need for spoofing a particular provider or operator in the UK. We could also do cell find and search by country. So for instance, if I was to punch in Belize, because I feel like being the NSA today, then I could list the countries that the operators in Belize and set my BTS configuration up to match those. So I would set my cell config up, and in this case, I'm going to spoof a well-known provider here, and essentially set it up so that it's simulating that, so that I can access the subscribers for an Android and iOS device, which I have inside of the Faraday cage. And it's important to point out that everything that's going on is going on solely within inside of this environment and isn't actually affecting anything else around it. So we have a couple of commands that are available here, and I'm surprised that that's actually shown. Okay, so I'm just going to quickly go into here. Okay. So essentially, we've got this Android phone which is powered up in the environment, and the GreedyBTS has identified the phone's IMEI and the subscriber identity, but at this point in time, I haven't actually given them any service. So I'm going to go ahead and just sort of leave that for now. It could take a while eventually because it'll sort of time out and wait and then redo things, so we might reboot it. But if we were to look at the additional commands that we have here, we could look at dump association. And what this allows us to do is it allows us to make the association by the Android phone is connected to this particular subscriber. So one of the things that I can now do is I know that this subscriber matches this equipment identity number, so I could actually begin to provide service based on the IMEI. So one of the things that I will do, and I'm going to kick this off now because it can take a while, is essentially punch in an IMEI. And earlier on, we used the IMEI of an iPhone as an example. So basically, what GreedyBTS will do with this regex is it will sit there and it will wait. And whenever it sees an iPhone, it will work out a free extension, and it will find the subscriber identity, and then it will automatically give that user service because it's matching the fact that it's a known iPhone. So what I'll do now is I'll just power the iPhone and let it automatically join and be provisioned. Oh. Just to show that it's not, if I was to punch in show service, the show service command shows us all of the users that exist currently in the database and their extension number if we want to dial them. Okay. So for instance, at this point in time as well, we can go ahead and give service to this user. We can just add them into the database at this point and then give them a kind of hard-coded extension. What we could have done is we could also have used a number of the other commands, such as the watch service. We could have given the regular expression to provision IMSs. And what we could do there is we could say, OK, well, I want to provide everyone who's got a Chinese phone in the area. I want to give them access. So anyone I know who's on a Chinese provider with a roaming agreement, I could just provision them. Or, for instance, a particular network operator, we could provide them. So in this case, we'll just basically automatically set them up and provide them. And I'll also provide this, and we can see now there's 2 subscribers in the database. Basically, what's happened is it's identified the iPhone user based on the IMEI when it's attempted to synchronize with the BTS, and then it's automatically provisioned it into the database for us. And we have here the 2, so we've got dump associations. So we can see here we've got 2 devices and 2 subscribers. Now, one of the things that I'll do is I'll run the output of the fingerprint command. The fingerprint command will basically look up the information from the equipment identifier and tell me information about what kind of phone it is. So I know here that I've got a HTC Wildfire and I've got a iPhone 4S, both within the environment, and both should have service. So I'm just hoping that the iPhone is going to come back alive. And why is it? So I forgot to restart the BTS when I changed the configuration. So, okay. So essentially now we can see the iPhone is online and it's got a GPRS connection. It's now dropped offline. Hopefully, yeah, okay. So it's basically come back onto the air. It's got a GPRS connection. And if that user was to attempt to browse out to some website, they would essentially see a kind of loading page. And what I'm going to do now is I'm just going to make a phone call using the other device. Make a phone call to the number, sort of 600, I guess. Connection valid. Okay, so if I just leave that user making a phone call for the moment. Okay, so essentially, if we were to look in the call recordings directory, the phone call that the user's made has automatically been recorded, which also includes the content of what they're accessing. So we're just going to basically copy that material off the device so that we can access it. Okay, so essentially, this is what the user would have heard when they were trying to make a phone call, which is Rick Astley's never going to give you up. So anytime somebody tried to make a phone call within the area that you're affected, you can sort of redirect them with asterisks, and obviously that kind of opens itself to all kinds of hilarity. So yeah, but on a more serious note, I could have quite easily spoofed a bank and then said, okay, please enter your 16-digit card number before I authorize you, and spoofed another kind of telephone IVF prompt or similar, and then automatically recorded that information as well. Okay, so this is the IP traffic that's going over the RF interface as well. So this is the iPhone trying to communicate out to various websites. And basically what's happening here is we're just provisioning it and giving it IP and then just routing it through our usual outbound internet connection. And from here we can do things like traffic analysis. We can start to record, look for session cookies, any kind of plain text information leaks. Anything that we really want to find in the phone or the traffic is pretty much exposed to us. So this is almost like attacking a device on an insecure Wi-Fi environment. And what's bad about this is if you actually look at the phone, there's like no alerting whatsoever. It's just like your phone normally looks. And you can essentially then begin using the IP interface or the IP address, and we can start trying to leverage attacks against traditional mobile services and browsers and the like. So if I run this show IPONE command, okay, I was worried that this might not work. Now basically it's temperamental to get the exploits to go, but basically what this does is it will sit in the background, and every time it sees an IP packet request coming for apple.com, it will essentially try to log into the device, and if it's jailbroken and it hasn't had the default credentials changed, it will log in and extract the address book, the SMS, and the photos from the device, store them within GreedyBTS so that I can recover them later. You could also try to use the Android JavaScript interface by injecting that into a web browsing session. But the one thing I'll say is it does take a significant amount of time. I mean, for instance, to extract a couple of photos can take several hours because of the speeds at which you're operating. It's not such a big deal if you place a device like this inside of a target's home environment or their office environment or an area where they're going to spend a lot of time. And then hopefully we'll just see. So it says, okay, so here we can see that it says the host is alive. So it's sent a ping packet, it's got the host being alive, and then it's going to essentially try to do this SSH login. And that will just continually run in the background. So every time it sees an iDevice, it will just systematically keep trying this exploit against it. I guess we can leave that running there for now just to see if it actually completes, and I'll get to the conclusion. There we go. Okay. So this is kind of basically the conclusions that I wanted to make from this, is that the information that's sent over your mobile phone is probably not as secure as you think it might be. And the fact that GSM attacks have been around for some time, we still have very little in the way of defensive mechanisms that are widely used. The ones that are in use are really more aimed at power users or people that are very technologically minded. They also require active use, and not all of them are going to be very effective. The only real surefire guaranteed way of detecting if someone is intercepting is to make one call on your original network, test if encryption is there, and then make a call on the fake environment and then see whether encryption was turned off or not. And that only really works if someone's interested in your call content. They could also be trying to get access to your data, which is using different encryption, which is going to be using different protocols within that, and it's still going to essentially expose information that you may not have thought you were exposing. If you're sending sensitive information such as usernames, passwords, or other material, then I would consider not using a wireless technology. Horse Messenger sometimes works. Or you could basically, send it in another way. And an attacker could basically use these environments to launch attacks against your mobile device without you being aware. And that we really do need to push on for increased baseband security enhancements and access to cellular data. So my email address and contacts is here. I'm going to open up for a few questions now. And I just wanted to very quickly say thank you to all of the people that have been out there doing open source and general security research communities in making these kinds of environments and tools and things more accessible so that I could look at the impacts and effects of them within a kind of contained environment. In particular, a note to MWR Labs, who I started doing some of this research when I was working there, and then also the Osmocon and Range Network guys who have been pretty awesome in some of the tools and utilities that they've created.